Hi guys, welcome to this new series of tutorial we are working on. It is the first of a completely free courseware. So we are talking about Embergen from JangaFX. It's a new fluid dynamics simulator, and we are going to show how to use it. Janga is developing a series, a suite of software. We have different software, some of them are actually over the market. Embergen is still under development, so let's see. It is a real-time fluid dynamic. The other software is vector ray generator. It's a force field generator, and it can be really useful to be used with Embergen 2. It's still under beta testing because it's under development, but it's really powerful, really fast, and we will see how to use it in production because we have a lot of features that are production ready at the moment. So it was maybe at the beginning it was more useful for real-time stuff, but actually the features are really powerful, so we can use for video games and film and stuff like that. You see there some of the customer, so you see a lot of big customer are using the product in production, and here you can see some example of the Embergen simulation, and you see that actually it can work with particles and fluid dynamics. It's really fast, so for example here you can see that it is using, for example, a GTX 1080, so it's not a so powerful GPU, but it's enough to simulate in real time stuff like that. Essentially the main problem will be the GPU memory, and we'll talk about it in this mini series of tutorial we are preparing. So we have to start talking about fluid dynamics. That's not a complete effects course, but it is useful to start introducing some information. Fluid dynamics is based on some algorithms and some techniques to simulate this kind of stuff. We have different tools over the market, so there are many solutions actually we can use, and I'd like to talk about it in general. So let's start playing with some. Okay, so the first idea, we have a simulation, and the simulation with this kind of algorithm is based on the domain. The domain is a 3D space, and the simulation needs to be simulated in a 3D space. Let's imagine a 3 meters for 3 meters for 3 meters box. The explosion or the cloud is inside this volume, and we can simulate just inside this volume. It is a nice way and nice techniques to make simulation, and you have to imagine that this space is split in another sub-level of spacing. So let's imagine that everything is based on little boxes, you see. Okay, so the idea is that the single box is a voxel. This is something like like the pixel for images. It is called voxel. Okay, it's the same. If you have a 2D image, you have the pixel. If we have a 3D volume, we have the voxel. So the resolution is based on the voxel scale. So if we have a lot of voxel with a small scale, it will be high resolution. The voxel contains data, for example, density, velocity, temperature, and stuff like that. And the information is moved from one voxel to the other. So that's a really nice way to simulate, because we can decide the resolution of the voxel and we can accelerate the calculation. And in this way, it's simple to decide the resolution and the quality of the simulation. But on the other side, we have some kind of problem. For example, where we have no data, for example, in the empty space, we have to take care about some information. So we'll need memory also to maintain empty voxel. Okay, so that's not so nice, because it means that if we have a huge number of voxel and we are not using the voxel, we have a lot of memory. Let's imagine a GPU with 8 gigabytes. We'll have the possibility to have an amount of voxel. If we have, for example, 24 gigabytes, we can have a higher level of voxel. And for example, the 3090. And if we have 48 gigabytes, let's imagine the A6000, we'll have a huge amount of memory, and we'll be able to have a really high amount of voxel. And using a voxel, it means that we can have a more complex simulation, higher resolution, more details and stuff like that. So let's think about it, because the heart about the simulation with the domain is the voxel. We have different ways to control it, so it is not the only way to simulate stuff, because for example we have the sparse algorithm that it's a really nice new technique. It will create and generate the voxel space based on the simulation, so it's more powerful. By the way, we have different tools over the market. Let's pick a color. Okay, if we talk about fluid simulation, we have Embergen, and we are going to talk about it today. It is completely GPU based. On the other side, we have solutions that are based on CPU, or in any case, we are talking about mixed simulation between CPU and GPU. So, if we like to make a list, we have, for example, Bifrost with the Aero tools, and Bifrost is available for Maya and 3ds Max. Then we have Phoenix from Chaos, and Phoenix is available for 3ds Max and Maya. And I don't remember if it's available for other software. By the way, we have FumeFX, and FumeFX is available for Maya, Max, and Cinema 4D, for example. And we have then Houdini. Houdini is obviously the most powerful solution for effects. And for Houdini, we have some acceleration inside for using a GPU, but we have also Axiom. I think I wrote in the right way. By the way, it is a free plugin for Houdini with a GPU solver, so it's really powerful. We are talking about the most used solution. By the way, we have other solution. For example, we have Magma Flow for and other tools for Blender. We have X Particles for Cinema 4D, and we have, for example, Storm, that is another standalone tools that now has grain and also gas solver. By the way, Embergen is still the I think the only that is based on GPU, mainly on GPU, just GPU. So we have maybe the most used are Phoenix and FumeFX and Houdini, but Embergen is going to be really, really powerful. So it can be a really fast solution to solve fluid dynamics stuff. So that's the software. Okay, so it's just launched, and you see we have some panel. UE is still under development, so actually that's the actual beta, but they are developing a new version with a new UI, new renderer, new solver, and many new tools. So that's the actual version, and you see that it is working real time. It's the 0563 version. We are using 4 gigabytes for the simulation, and I have 8 gigabytes on my 2017. And then we are using 40% of GPU to simulate in real time and render in real time. And you know, that's a renderer, so it is working in real time to render the simulation that is calculating in the same time, you know, so it's simulating and rendering. Then we have the render time at the same time. We have 6 microseconds for simulation and around 5 for the rendering. And the frame rate is the how the UI is interacting, and actually everything is moving really fast. You see that I can use the Alt key to orbit. You see that everything is real time. It is simulating, and I can move the stuff during the rendering. Here you see that it is cut because we are inside the domain, so the voxel space. We have some tools inside the viewport, and obviously we have some debug stuff, and we have some features to see in a better way the rendering. You see that the panel can be scaled. That's the node graph. Here we have the scene. Actually, we have all those nodes that are created in the scene. If we pick a node, we have inside the node info, we have all the parameters, and there we can control the animation. So, we were talking about the cut over the domain. We have the possibility to see the domain. We can click over show bounds, and you see that now we have a different visualization. So it's clear where we have the bounds, and that's the domain. So obviously when the simulation stuff goes out of the domain, we have no simulation and no rendering. We have, you see, the possibility to pick the emitter and moving the emitter in real time, and everything is still continuing simulation in real time. You see that if the emitter is out of the domain, obviously we have no simulation. When we are inside the domain, we have the simulation. By the way, it's really amazing to work in this way. Everything is real time with a really nice quality. Actual resolution obviously is not so nice, but it gives us the possibility to work in real time. You see that we are using the ray tracer. We have the possibility to export stuff, preview stuff. We have many tools. For example, here you see that we have the settings for the viewport render. So we have some really a lot of parameters, but we have the possibility to decide everything, choosing between different level of quality for the viewport. Everything is better than before, but you see that simulation time is still the same, but render time is slower. So we have a better quality, but it is slower. So that's nice for some stuff. For example, to check how the simulation is going, how the look is going. But you know, when you need to take care about parameters and solver simulation, it is better to take care about a lower quality level for the viewport. So let's go back to the basic level. So you see everything is fast enough to take care about every single parameter to understand how it works. So I think that this way is amazing. Obviously, if we go really near to the volume, we'll be able to see the voxel. So you see that we see something like boxes with a blending between them, and that's the voxel. So we need, you see, it's something like pixel over an image. Obviously it has a really nice blending, let's say blending, but it's something more complex to manage the rendering, but it's visible. If we go really far, obviously it is enough. You know, the quality is okay. So if we are talking about something that is distant the camera, it works. If we need to go near the simulation, we need a higher resolution, so we need a higher level of voxels. So it is something we have to take care about, but we have to understand which is the level of resolution we need. Here you see we are talking about 7,000 simulated frames, so it is something amazing. If we were talking about another 3D tools with CPU simulation, it was impossible, you know. So here we have the possibility to play. So you see that everything starts again. And if we like, we can start from scratch again. It's useful when we are going to change something about the emission moment. So we need to start from zero again the simulation. So that's the node graph, that's the interface. It is going to be rewritten, but it will be similar, more professional with more tools. We have, for example, more the back stuff like the velocity. So you see that we have some vectors showing the velocity and also the temperature, because we see the color, for example, something like bright yellow or white for the high temperature and black for the low temperature, or we can decide to see just the temperature. It's really clear. By the way, we are going to have more the back stuff and the higher quality the back stuff in the new release coming in, I think, in coming weeks. Okay, so the first idea is to understand how the software is working and how the node graph can explain the scene. So that's the node graph. Let's scale a little bit the viewport, and let's focus on the node graph. You know, we can pan and zoom using the scroll mouse. We have the possibility to select nodes. Every single node has input over the left and output over the right. Everything in this node graph is essentially the scene that we have actually. So connecting the nodes, we are going to change how the scene is working. So for example, here we have the emitter. So that's the emitter, and we have the shape of the emitter that is connected obviously in input to the shape. And in this way we can have different emitters. We have basic shapes, we have the possibility to have meshes coming from other software. They are providing the possibility to add FBX, Alembic, USD, so it will be really powerful to interact with other software in the pipeline. So it's something we need to have a more complete control. And you know that the emission can have a force. So in this case, for example, we have a noise. In this case, we have the emitter that is going as an input in the simulation. This is the main node. It's essentially the solver, the fluid solver. So you see that we have a lot of parameters about the dynamic and all the properties the solver can have. Also the particles, obviously. And we have the possibility to have forces inside the simulation, colliders, so we can have meshes to collide. And everything that is simulated inside the solver can be exported with the export VDB nodes. So we can export in VDB file format, and then we can render the stuff with any other 3D software. Or we can move the data in the volume. The volume is something that is used by Embergen to show the volume in rendering, so to shade. Let's think about the shading. So we have the light sources, and we have the possibility then to move the stuff in the render. That will go in the scene, and that's essentially the rendering properties. The rendering properties will move pixel to the capture. The capture is able to capture the viewport using the camera, obviously, and all the data coming from the scene, and all the parameter will be captured in the RGBA channel and exported in an image. So we'll be able to render sequences and flipbook using directly the Embergen ray tracer. So something really fast and really powerful to export stuff. Or we can decide to export the simulation, move data in other 3D software, or also composing software, or maybe Unreal or whatever else, and render externally everything. So we have different ways to decide how to move. So something we can done is to reset and use the preset we have to make an export in VDB. So here in the panel you see that we have the possibility to choose the file name. So we go in the folder where we have the project we are working on for this tutorial series for the lesson 1. You see everything written in Italian because, you know, the first language for the series is Italian. By the way, let's go for smoke underscore. We have the possibility to have absolute frames. By the way, for the moment it's not a problem. We can go with the stuff we have now. So first frame we go for 0, and last frame we have 64. So it means that we are going to export 64 frames. You see here we have the selection. So let's go for 100 frames. Let's go to double check. We have the fields we have to export. For example, density, we have the temperature, we have the possibility to export the fuel, but this time it is not useful. We have the possibility to export the flame field and the velocity. And talking about the velocity, some software are able to export just one field with both 3 axes. And this time we have 3 axes separated. We have the compression, but we are not going to use it. And then the coordinates. We have the Z up and the right-handed. So the X positive is to the right. It is okay to export in this way. For example, we have 3ds Max that works in the same way, but other software needs to use the Y up and the X to the right. So you can rotate the VDB, but it's better to choose the right one, so you don't need to take care about rotation, and it is useful to do it. So let's say Y up and right-handed for the X. So in this way it is set in the right way. Okay, we have centimeters for the units. And then we have a threshold for the data that will be exported. By the way, let's go with this simulation in this way. So I'm going to choose the folder where we are going to export the stuff. So we'll be able to see the frames during the exporting. You see that's the empty folder. Okay, export. It is going a little bit slower than before. And that's just because it needs time to save the data over the HD. So it will be useful to have a really fast HD or maybe an SSD to load and save the cache. In this way you will be faster during the simulation, during the exporting, and also during the loading. And then you see that it's going again faster than before. Okay, it is done. You see that here we have the frames. We are talking about a really small volume exported because we are talking about maximum 6 megabytes, and caches can be really big. I mean, maybe 100 or hundreds of gigabytes. So we are going to open the stuff in Claris, but you can open the VDB everywhere. It's not a problem. It is just to see how it works and to see if it is simple enough to do stuff like that. So geometry, let's go to import a file for volume. We can write smoke, just a little bit of more space, and then we can choose the file name. We go to select the first frame we exported before. So in the right folder. Okay, now we have to say that this is a sequence, so the text sequence, but it is not able to understand which is the last frame. Let's go with a 99. We set to 99 the final frames in Claris, and then you see that it's loading something, but the position is wrong because maybe the origin in the Embergen is different actually. Okay, let's move up. Okay, you see it is loading. It is working perfectly. Maybe we have to take care about scaling, but actually it's not a problem. So it is just to understand how it works when you go to import stuff inside other software. So the density property actually is density. It is able to give you the properties to render the smoke. Then we have the flames. So we'll have just flames in this field. We have the temperature that is useful to render the fire and the flames. So we exported it because it's useful to control the shading. And then we have the 3-axis velocity. In this case, the axis velocity are separated, so it will be the best way to have just one field for both axes. It is something that, for example, Houdini can do in a really simple way, controlling, preparing a really simple network. Maybe we'll see something about it in the future. And by the way, they are taking care about it, so in a coming version we'll have the same in Embergen. So we don't need the velocity because we don't need to render the motion blur. So let's go to add a new light, an environment light, something to simulate a skylight. We got to take care about the rendering resolution, and then the camera position is wrong. So we have to move it. Okay. General look is bad because we have no material actually. So we are just visualizing the VDB. So let's go with the material and volume material and apply. Okay. Everything is changed because now it's the volume shader that is controlling the rendering. We have a new layer, a black layer here, so we'll have the black background. Let's give 50% quality to the sampling. Then back in the render, let's go in the volume. Let's say that we'd like to have a physical way to control the shading. And then you see that there we have the density multiplier, so we have more density for the smoke or less density, so you can manage the density in rendering to achieve a different look from the Embergen stuff you saw before. You see that the low quality is visible because we see the voxel here. So again, we created something really fast, but the number of voxels is really low. Okay. Let's go to see maybe how we can control the emission. So we go in the material, the node material. So we need to pick the emission. To pick the temperature to control the emission. It's simple enough because Chorus is really simple to do stuff like that. So we are going to pick the data inside the field and we'll go to control the emission in the shading. So we'll have the fire and we'll have also the illumination scattered by the through the smoke by the fire. So let's go to create some nodes. The first one is essentially the black body. So the black body is a way to control the emission and the coloring using the temperature. So you see that actually everything is white because the temperature is set to 5,500 degree, and the temperature is the same all over. So we need to pick the temperature. We go to use the extract property node to control the temperature. Okay, we have back the same visualization we had before. So this node needs to pick the field. So let's go in the property name and we pick the temperature. You see that we have the fields we had before. We have to scale down how the temperature is controlled. By the way, you see that we have the energy compression that is able to take care about a more artistic way to control the coloring. And then we have the possibility to go back to a lower temperature scaling. That's just a way, but we have different ways to control how the temperature is peaked. By the way, let's go with 30%. Back in the volume, something that needs to be done. Let's set to off the skylight so we see just the lighting and the scattering. That's the main light, something similar to a sunlight. So let's go for 0.5 for the angle. And then we need to have an higher exposure, let's say 1.5. So we have a little bit more lighting than before. Everything is black there because we have no lighting, and the scattering is off, and you see that also the fire is not scattering lights through the smoke. We need a higher level of bouncing inside the diffuse. So you see that this material, the volume, has a diffuse depth. Now it's set to nothing, so it means that it's going to use the full value from the renderer. But we need more bouncing, because using the bouncing we can give the right lighting and scattering it to the smoke, and also about the fire. So the best way is to control it just over this material, because we have this value also in the essentially in the path tracer, and in this way we can say how many times we like to scatter rays inside the smoke. The value for the path tracer is there, the sampling. Okay, in the indirect path you see that we have just one bounce. Okay, so the light can go inside and we'll have just one bounce, so we have essentially no scattering. So we get the material, and just to start we can use, for example, 25. So we start to have the bouncing inside the volume. You can use higher value, for example 50 or something like that, to have a better lighting and better illumination. It will take obviously a little bit more time, but the final result will be better. We can have back the environment light. Let's use maybe a color similar to a sky, so it will simulate essentially a dome to simulate the sky, but it's really simple. Let's go lower with the exposure to -2, and maybe we need a little bit more light for the main light. You know, the quality is low for the simulation lighting. It's really simple, so don't worry about it. We are not creating the look depth here in Clarice. It's just to see how the volume simulated by Embergen can go outside to another software. We have a lot of grain, so we can take care about the grain. Let's go for material sample to 32, but we can just use the automatic maximum sampling. So we go for 1000, and then we go to have just 0.005 for the noise threshold. It will take just a little bit. We need 100% sampling, so it's final quality, and then it will take care about the rendering. We'll have no grain, but please remember that the quality will be low, because the simulation is not so nice, you know, and we are controlling nothing about the shading. You see that we can, for example, just move up the density if needed to have a more pyroclastic smoke. It depends on the final look we like to have. We have also the scattering to be controlled, by the way. That's the result. You see that the noise is lower, but the quality obviously is based on the simulation. Let's set to pause. So let's go out of Clarice, and we can go back to Embergen. So it was nice to see how the simulation can be exported in other software, but now I'd like to focus a little bit on the quality. So if we go near, you saw that the quality is poor. So we see the voxel. It is something that can work when we are distant, but in this case we have to take care about the resolution. And the first thing is having more voxel. So inside the simulation, you see that the first part is the essentially the size of the volume. We have various parameters to control the size and the voxel quality. First of all, you see the proportion. We have the actual sides. We have 12 meters, and then 25 meters over the height. and we have 128 and 128 voxels for each side of the base, and then 256 for the 8. And then we have around a total amount of 4 million voxels. That's not bad. It's really fast to be calculated, and we need just 3.5 gigabytes. Okay, so we have the voxel count there. We can change the voxel, just the voxel counts, or we can change the bounds for the minimum over one axis to the maximum. Okay, so if we have, for example, the possibility to control the voxel size, actually it's 10 centimeters. It means that the minimum cell size is 10 centimeters, so it's really high, and that's why we have a really low quality. So we can take care about the quality with the voxel size, but we have also the upscaling. Upscaling is a really nice technique to have higher quality. Upscaling the simulation. So where we have, for example, one voxel, we'll have more voxel inside the same space. By the way, if you like to have something more realistic about the vorticity and how the fluids will behave, it is better to have a higher number of voxels. So the first parameter, the voxel size, can be lower, and in this way we'll have more voxel and we'll have a more complex simulation with more details. Okay, so that's the best way to achieve. By the way, upscaling is also useful. So let's go half scaling for the voxel size. So we go for 5 centimeters. It means that actually it is going to have a smaller scale to maintain the amount of voxel. And you see that the minimum and the maximum bounds are changed. So let's go back to the minimum 6, maximum 6 for both X and Y, and the minimum 12 and maximum 12 for the Z axis. So we'll have the same dimension and proportion we had before. So I mean it's 12 plus 12. Okay. Now I can say that we are requesting to have this new dimension, so we have double over each axis the voxel amount, and we are talking about 33 million voxel. So it's a lot more about the actual one. Let's click over apply new resolution, and that's done. So that's the new bound, same scaling, same size, but the quality will be higher. Okay, you can see more details. We have more GPU memory used, but we have a lot of more details and vorticity. GPU is more used, and we have a slower simulation. It was 5, now it's 36, and we have also a little bit slower rendering. But you see that the quality is really, really higher than before, and it is still really fast. We are talking about an RTX 2070, so it's something that can go really, really fast, for example, over an RTX 3090. By the way, the quality is amazing, and we never touched anything about the simulation. So that's the default, and the default is giving us this kind of simulation. I mean, that's really great. Okay, let's stop. So the idea is to see, okay, you see that the quality is really high. Here we have the cutting, that's normal. By the way, we have the possibility to say that we like to have the blocking. So you see that we have the blocking over the minus and plus over each axis. In this way, we'll have collision between the smoke and the volume bounds. So let's say that we like to stop all over. Just the ground is not stopped because I think we have a little bit of intersection between the emitter. Reset and simulation. Everything seems like before, but we'll see some differences as soon as the fluids will touch the bounds. So we should see something now. Okay, you see that we have the cut, but we see the smoke rolling over the bounds, and then it is also bouncing back. We'll be able to see in a better way over the top on the ceiling. By the way, you see that we have the sliding and the collision. By the way, okay, over the top is really, really visible. You see that the smoke is going back down because we have the collision and we have the sliding over the bounds. I mean, that's amazing, really amazing. And everything is done using the same memory because the voxel is the same. And that's the good stuff for the voxel. And you know, it's also the worst part of the voxel based, and the space will be more efficient. By the way, let's set off the bounding collision. You see that it is reacting in real time to the changes we done to the parameters because everything is in real time. Nice. Let's stop and reset. So next thing we can do is to go back and see what's going on if we go lower, just to see what we can do with this kind of GPU. So we're going to 2.5 centimeters. We use the same scaling we had before for the bounding, and now we'll have trouble with this resolution because you will see in a few that we are going to use all the memory we have in our GPU. So -12 and then 12 and apply. So you know we are talking about 250,000 million voxel. It is a huge amount, so it will create us a little bit of problem for sure because we're talking about a really huge number. By the way, it will be not just a problem of velocity, it is a problem of memory. So apply, and now it is using the memory. So we have around all the memory used. So it is really complex to manage. I think you will see maybe some problems also during the recording and maybe the webcam, because you know the UI is still refreshing, but it is going to be really, really slow and really unstable because we have no more memory. We have no memory for the visualization. We have no more memory for Windows. We have no more memory over the GPU. So you have to take care about this value. You have to take care about how much voxel you can simulate. That's the only problem we have because the software is still really fast. Okay. I had to reset. You see, I had to stop. As I said, it's becoming unstable, so I'm trying to stop and to set the new value, and now I'm trying to use 3.5 centimeters. So we have just a little bit less memory used, but in this case, the workstation is still able to simulate, and the amount of detail is amazing, really, really amazing. You can see that the simulation is still really fast. We are talking about 75 microseconds to simulate one frame, and you see a lot of vorticity. And again, I never touched the vorticity, so that's what we have without going to control how the vorticity will look. So, for example, something you can do is to have a lower voxel size, and then maybe using a little bit of upscaling to find the best compromise between both value. You know, if you have enough memory, obviously you can rise up the quality with the really low voxel size. By the way, let's set to stop. And we can go back to 01. Sorry, I'm using the mouse, so I have to take care about a better resolution. Let's set back all the scaling to the default value. So -12 and +12 and apply. Now we are back the first resolution, and this way we are working really fast because it is real time. And we are able to take care a little bit about some feature. Okay, so let's reset. Set to pause. Okay, let's see something about the emitter. That's the main emitter. It's something like a container with all the information for the simulation. For example, the possibility to see the the emitter, that's the mesh that is going to emit the fluid. It's a torus, and here we have the shape. You see that we have the sphere, the box, rounded box, the capsule, torus, cylinder, rounded cylinder, tube, cone, rounded cone, ellipsoid. And then if we go to create a new node with a right mouse button, we have the possibility to create a new category there, and you see that we have something else like the particles, modifier, mesh, and we have a lot of stuff that can be used. And we are going to see some stuff. For example, the mesh is able to load mesh from outside. Soon we'll have the possibility to use FBX and Alembic, and it will be amazing. We have the transform value for the position and rotation, so standard transformation, and it is nice to have it. Obviously every parameter can be animated. We'll see the animation in coming lesson. And you see we have some parameters about the radius for the torus. Let's try something like that. Okay, let's select the connection between the noise and the emitter. And in this case, it's force for the emission. So you see that the emission now is regular. We have vorticity, and that's normal because the solver is creating vorticity, but we have no turbulence during the emission. You see that everything is really regular, and then we have the vorticity. So that's a way to change how the stuff are emitted. Okay, let's go to connect, for example, this one to the solver. Okay, now the force is applied globally to all the voxel. So you see that now we have noise over the emission, and we have noise over the other voxel too. So that's different than before. Okay, so it is not changing the emission, but it's changing how the entire solution is behaving. So let's remove the connection again, and let's reconnect to the force emission. To be faster, you see that again. Now we have the emission with noise. Really nice. The noise force has parameters, for example, the scaling. So now you see that the formation is bigger because the noise scaling is bigger than before. We can have more octaves to have more details over the noise. So we have the possibility to control it in a really nice way. And again, everything can be animated. So we have a huge control, and you see that the quality of the simulation is still amazing. And we are just using a torus and the turbulence. That's all, you know. So let's imagine if you have time to control the simulation, what you can do. We have obviously the possibility to make it behave like an explosion. We can control animation, we can control expansion, we can control everything. In coming lesson, obviously we'll take care about more stuff. First of all, we are going to talk about the emission and the forces that are really important. We are trying to give you the possibility to be productive with this series of lessons, and be able to create some really nice effects using the Embergen, and understand the basic of Embergen, fluid dynamics, and how the power effects can be simulated and rendered. So we hope that it will be really useful for you. So thanks for watching, and I hope to see you back on our YouTube channel to see more lessons about Embergen introduction course. So thanks again. Bye.